started the topic of components of a traffic system. There are 5 components: road users, vehicles, streets and highways, and traffic control devices, and the general environment. Okay. In the road users, the most two important people are drivers and pedestrians. For drivers, we have two important characteristics: the visual acuity and reaction process. So for visual acuity, we looked at different functions which are performed during the driving by the eyes, and we also looked at different fields of vision. And then for perception reaction process, we measure it in terms of time, and that time depends upon the expectancy of the situation. Unexpected needs more time, and vice versa. And for pedestrians, our main concern is their safety, because they are very vulnerable to injuries, serious injuries and deaths. So you can provide them a safe passage from the road by giving them a signal. And if you provide a signal, then we need to know their walking speed. Okay, so this is what we discussed, and these are some of the facilities which can help them to cross the road safely apart from the signal. Okay, now today we will discuss the vehicles. So according to AASHTO, vehicles are divided into 4 categories. Okay, we have passenger cars, buses, trucks and recreational vehicles. I mentioned earlier that we discussed 2 of them, right? Or we merged them into 2. Okay, which were what? First one is passenger cars, and the other 3 are what? Heavy vehicles. Okay, and another name given to these 2 types was what? I mentioned in the last lecture. We said passenger cars are what? Personal. Okay, and the others are commercial vehicles. Okay, but they are the same thing. And one more thing which you can see here: AASHTO deals with the design of the road. AASHTO deals with the design of the road. So they have more categories here, and even within each category you will find different subtypes. Okay, because for design it can be important. Okay. You're talking about the design of the road, the geometric design of the road. So that's why you see more names here, okay, than what we have seen with traffic flow. Which vehicle characteristics are important for us? Braking, which basically means deceleration. Okay, we have acceleration, we have low speed turn, and we have high speed turn. These are the 4 things which are important for us in terms of design. 4 characteristics for design. What are the things which can affect these characteristics? We have the size and the weight and the operating characteristics of the vehicle. Now size and weight are directly proportional, right? Bigger the vehicles, it will be heavier, right? Okay, and the heavier it is, it will be slower as well. So deceleration acceleration rate is lower. Okay, so they take more time basically. These vehicles will take more time. Okay, what about their turning? They will take more time and more space. Okay, so the size and weight has a direct relationship with the travel time of these vehicles and the space taken by these vehicles. Clear? Okay, then we have operating characteristics. Operating characteristics is basically the mechanical power or the operating mechanism of the vehicle. Okay, the engine basically, the engine. Okay, so and the operating characteristics can cancel some of the effects from size and weight. For example, you take plane and a truck. Okay, now which one is bigger? A plane is bigger, right? And which one is faster? Plane is faster. Okay, but we said bigger means slower, right? Why the plane is faster in spite of being bigger? Because it has good operating characteristics. It had a jet engine, right? Okay, so the engine can cancel out the effects of size and weight and can affect the deceleration and acceleration in these things. Clear? On a highway, when you're designing a highway, we have to select our design vehicle. I already showed you 4 types, right? 4 main types of design, 4 main types of vehicles, which are what? Passenger, pedestrian, driver, heavy vehicle, buses, trucks, RVs. RVs are recreation vehicles. The vehicles which have everything behind them, like a small house. Okay, everybody has seen it, right? What you were saying? You were saying like you have seen it or you have it. Yeah, you have seen it and you have it as well. No. Okay. Basically, you can sleep in those vehicles, right? You can sleep in any vehicle, but don't. Okay, so, and I showed you within these 4, then there are subtypes. Okay, when the highway is working, it's operational, you may have 20 different types of vehicles which are passing through the highway. Okay, so we have to pick one because we cannot design for multiple vehicles at the same time. It's the same highway, it's one highway, so we need one design vehicle, and that one design vehicle should be what? Which one? So it should be if you have 20 different types, which one should I select the design? The bigger one, the slowest one, biggest one, okay? But if you remember, when we were discussing driver characteristics, we said we take which percentile? 85. Why not 100? 100 is the highest one, right? So we don't go for the highest one. Never, right? So it's the same case here as well. We don't always go to the highest one. Okay? So if we have to look at the percentage frequency of that vehicle in the total traffic. Okay? In total, compared to the total traffic, what is the percentage of these vehicles in the traffic? Okay? So it's not only about the size. I have a very, very big truck that only comes 1% of the times. Okay? So if I ignore that one truck, how much traffic I'm ignoring? 1%. Okay? So in this way you can ignore up to anything less than 5% can be ignored. Any vehicle which has less than 5% traffic can be ignored. You can take the next best thing. Okay? So if I have a very, very big truck which has 1% and I have a smaller truck which has 7%, so that very, very big truck can be ignored because I will just ignore 1%, which is allowed. But that the other truck which covers 7%, I cannot ignore it because then it is more than 5%. Got it? Okay, so any vehicle less than 5% traffic can be ignored even if it has the biggest size. Some guidelines here about the selection of vehicle. The minimum design vehicle for any street, any highway, any road is a single unit truck. Okay, is a single unit truck, even if you are not expecting any truck. Even the percentage of trucks on that road or that street is, let's say, 0.1%, not even 1%, 0.1%. Okay, but you cannot go below or cannot take a vehicle which is smaller than a single unit truck. Why? Which vehicle has the size of single unit truck? Bus. So why would I take it for design? Why is it necessary to take a bus for design? It's a street, let's say. There is no bus. Which vehicle I have to accommodate in my design? Passenger car is not a truck, right? So I will take passenger car as my design vehicle. Yes.
In my design for the bus, I will cover all the things.
Emergency vehicle. It's written there. Did you read it or not? Nobody reads it. And then people are saying your slides are something else and exam is something else. Oh, I will do it from here. You still get 0. Whoever it is, you are not reading the slides. How does it matter? Right or wrong? You doesn't even know what I'm talking about. I'm right, right? Always, huh? I was thinking about cancelling the final exam. Right? Okay. So, to accommodate emergency vehicles, because even if there are no trucks, even if those emergency vehicles don't come in the area for many years, but when the time comes, they have to be allowed. Okay, like the fire extinguishers we have in the buildings. Okay, all public buildings have fire extinguishers, right? So even if there is no fire for many years, these fire extinguishers are still there, they are inspected, they are replaced, and so on and so forth. Okay, so this for the case of emergency. Then we have the case of design of parking areas, which can be done for passenger cars, no problem. Okay, because emergency vehicles are not supposed to go through the parking lots. If there's a problem, if there's an emergency in the building, we give a direct access to the gate, the main door, not through the parking area. Okay. Yeah. What are the things of the road design which will be affected by the design vehicle? First of all, we said about what? If the vehicle is bigger, it will need, or if the vehicle is heavier, it will need what? More space. Okay. So the width of the road is according to the design vehicle. Okay. Secondly, when you are designing the turnings, whether you are designing a curve or you are designing a turning on the intersection, it will depend upon the size of the design vehicle. Okay. What else? Yeah. The width of the road, normal width of the road is something else, and the width of the road on a curve is usually larger. Okay. Again, because of the design vehicle. A truck which may need, let's say, 10 feet when it's on a straight road, when it comes to turning, it cannot make the turn within 10 feet. It's too small. Okay, so it needs more space. So we call it lane widening. Okay, so some of the values are given here. I also showed you these values in the level of service topic. We had the lane width adjustment factors. Okay, so if you go to the tables, you will see the same values there. Okay, these values for us are like for a small street. Okay, 9 to 12 feet is our local streets. Okay, our highways are much bigger than this, even more than 3.75. Okay, we have highways which have lane widths more than 3.75. Okay, so now turning characteristics can be divided into two types: low speed turns and high speed turns. Okay, the difference between them, or the limit between them, is 10 miles per hour. Anything less than 10 miles per hour or equal is considered low speed. Anything more than that is considered high speed. Now, what's the difference between them? When the vehicle is moving, there are certain external forces acting on the vehicle, right? Like what? Centrifugal. Wind. Okay. Friction. What else? What other force acts on a vehicle? Gravity. Rain. See? Okay. Now, 2 days of extra rain, and people are thinking about rain is an external force. Yeah, external force. Yes. Okay, but what will happen to these external forces when the vehicle tries to accelerate? Will they increase or decrease? Their effect will increase or decrease? The effect. The effect will increase, right? The vehicle will need more force to increase the speed. Otherwise, any vehicle can go at 200 kilometers per hour, right? Okay. Why were we talking about the operating characteristic and engine and so on? Engine then doesn't have any effect. Okay. So we need a bigger engine to accelerate more, because the forces will also increase. The resistance will also increase. Okay. So that resistance is more in high speed. Okay. And the resistance is less in low speed. So in low speed cases, the resistance is almost negligible, almost zero. Okay. So if you are designing a turn for low speeds, this much value is even less than 20. This is less than 20 kilometers per hour. Okay. So in that case, the size of the vehicle is enough to find the radius. Okay, the turning radius can be found according to the size of the vehicle. That's enough. Okay, there's no calculation involved. And these radii are given in books as well as they are available with the libraries of the design software. If you're using a software for geometric design, you specify the vehicle, the software can tell you the minimum radius according to the size. Okay, and now you can see here the case of low speed turn and high speed turn. Low speed turn is happening where? Intersection. Okay, because the intersection you are supposed to slow down, and most of the cases you will stop and then make the turn. So it's a low speed turn. Okay, the high speed turn works. Okay, so it happens on the curve. Okay, so it's a curve. There is no turning here. I'm not going in a different direction. I'm on the same highway, but the highway itself has a curve. So obviously you will not slow down here. You will not stop here. You may slow down because of design, but you don't have to stop. Okay, so going from 100 to 90 kilometers per hour is still high speed. Okay, so the cases of low speed and high speed. This is a sample of the radii which is available for different types of vehicles, and it's for low speed. So you know the type of vehicle and you have the radius. Okay. So each type of vehicle has a standard size. Size is not written here, but in the background there is a size. So passenger car has a standard size which we have been using. If you go back to the previous equation, some cases we were using width of the passenger car and so on and so forth, or length of the passenger car. So it has a standard size. So all these types of vehicles have standard sizes. Okay, and this is just a sample because there are many other types. Okay, so you can see for each vehicle I have two columns. For each vehicle I have two radii, right? You look at the last one, radius of what? Inside edge. This is the radius of the inside edge. Then what is this one, the middle one? Radius of what? Center line. Okay, so you have the inside edge and you have the center line. You take the difference, what do you get? Huh? If I take the difference of these two values, I'll get what? Half the lane width, right? Okay, and why do we need to have the width here mentioned? Why width is mentioned? Only the radius should be enough, right? Why the width is mentioned? Already told you. Because of what? Huh? Sorry? No, it's not a range. It's not a. This is one value and one value. It's not a range. This is one value for the inside edge and this is one value for the middle. Okay? But why these two values are mentioned? Why not only the. So what? I already know this. Why do you need to tell me again here? I told you, heavy vehicles, they need some extra widening on the curves. So the width is there so that you know how much extra width you are supposed to give. So if I just tell you my lane width is 12 feet and my radius is so and so, you will make a lane of 12 feet even on the curve, which is not enough for trucks, for cars, for heavy vehicles. Okay, so you can see on the top, the difference is very small, right? It's less than 10 here. If you look here, it's more than 30 feet. Why? Because the vehicle is heavier, bigger. Okay, so the two radii are mentioned so that you know that you need to do some widening, extra width. Okay, they're showing the extra width we need. Okay, for high speed turns, we said that the external forces acting on the vehicle are increasing. Okay, so it's not a constant value now. I cannot fix the value of the radius. Okay, I have to balance the radius according to the motion of the vehicle. Okay, so this is the equation we are trying to balance. Okay, so the left hand side should be equal to the right hand side. If it is not, something will happen. I don't know. Something will happen. Okay, the vehicle will fly or fall. Okay, one thing or the other. You can try it. Okay, but something bad will happen. Got it? In the end, both sides of the equation are same as it is always, right? You have to match both sides of the equation, right? If they are unequal, your life is finished. This is what they have taught you, right? From the school till now. Both sides of the equation should be equal. See? Life equal to death. Very good. So, what do we have in this equation? We have E. E is superelevation. What is superelevation? Superman. What? A slope. Okay. Where do we give it? Where do we give it? Where do we give superelevation? Horizontal alignment meaning what? Everything is horizontal alignment. Curves, yeah. Curves is part of horizontal alignment. Okay. Anyway, so yeah, on curves we need to provide the slope. Okay. Again, what's the reason here? To give us extra force to push the vehicles towards the curve. So it's always towards the curve. So if I'm turning on the right hand side, then the superelevation will be towards the right hand side. So the vehicle has extra support in turning. Okay. So superelevation is providing us the positive push. Okay, that we need. Okay. Then we have F, which is the coefficient of side friction. F is the coefficient of side friction. Then we have S, which is the speed for which we are designing the road. Then we have R, the radius, which we are supposed to design. Okay. And then we have G, which is gravity. Okay. So now in this equation you can see we have a value which is E into F. Now E is the slope, which is in percentage 0.00 something, okay, or 0.0 something, a very small value. And then we have F, which is also in fractions. I will show you the table. So F is a small value and E is a small value. If you multiply two small values, what happens? It gets smaller. Okay. So two weak people cannot help each other. They should kill each other. Okay, or you throw them out. Clear? One of you should start eating, and not only chips. Okay. So E into F is almost 0. E into F is almost 0. So this can be taken out. Okay. Now what are we left with? We are left with the rest of the equation, and I want to calculate what am I designing? Radius. Okay. So radius should be on one side, the other things would be on the other side. Okay. So this is the equation I have got, but in this equation I have somehow put 15. What is 15? Conversion factor. Okay, very good. So I am converting what? Conversion factor for what? Okay, tell me. What did I convert? Speed. Okay. Speed from miles per hour to feet per second. So speed divided by 15 will convert it from miles per hour to feet per second, right? Includes the gravity as well. Okay, so the actual equation was what? R equals what? Tell me. R from this one. R equals to what? S square divided by G. Yeah, actual equation has G. 0.01 is because of the percentage. Okay, so you have to keep in mind E should be converted to decimals. Okay, so I'll just write E plus F. This was the actual equation. Okay, so in the end I had G. So G is 32.2 in feet per square seconds, and then I have the conversion of S from miles per hour to feet per second, which is 1.47 square. Why square? Because speed is square. Okay, so this ratio 32.2 upon 1.47 square will give you 15. Yeah, don't trust me. Okay, okay. So this ratio is basically 50. This one. Clear? Is it? Sure. Okay. Clear? Okay. And what happened in the last equation? What happened here? Foot to meter? It could be, yes. Could be.
Speed as well.
Huh? Yeah. Miles to kilometer. Yes. Yeah, the gravity will change. Okay, and what else? What conversion of what? He's saying foot to meter and then miles to meter and miles to kilometer. And second to what? Speed is in kilometers per hour, and I want the radius in meters. Okay, we don't do miles and feet. We did it in surveying, and everybody was failing. So now we don't do it. Okay. So speed kilometers per hour. We want the radius in meters. So everything else is in meter per square second, and we converted the speed from kilometers per hour to meters per second. Okay. So that's how we got 125 here. Anyways, so we had F and E. So minimum value of E is 0.5%. This is only given for drainage. Okay, so you have a turn which is very low speed, and we don't want any super elevation to resist the forces. They are no, like the forces are negligible. Okay, but I will still give a small super elevation for the purpose of drainage. We limit the super elevation up to 12%. Okay, to avoid the other extreme, that if you lift the vehicle too much, okay, if you give too much slope towards the curve, the vehicle may roll or fall because of the slope. Okay, so that's why we have maximum values as well. So normal maximum value for super elevation 12%, and if you have wet conditions, then we limit it to 8%, because normally we are just afraid that the vehicles will fall or roll normal, but in wet conditions it can slip as well, which is easier. Okay, so for wet conditions, we have snow or rain continuous, okay, then we limit it to 8%. Coefficient of side friction, we have these values which have been taken, but they are lab experiments. They the instrument, I forgot the name, but there's a very simple instrument, okay, this big, and you can just find out the coefficient of side friction for any surface. Okay, so it depends upon the surface of the road. And we do it, if you have to find it, then we find it for wet conditions, which is more critical. Okay, the worst case is the road surface is wet. Okay, and in the highway course there was a question as well, I believe, where you were supposed to find out the coefficient of side friction using some data from driving. Okay, so but in any case, F can be found from in the lab or from the road. Okay, and we have this table which they have provided according to the speed and normal surface of the road. Okay, so if we have to find out the radius of the curve, and we have a speed of 70 miles per hour, super elevation 6%, and F value 0.1. Okay, we can find the radius, right? Anything missing here? Nothing missing, right? Everything is given. Okay, now one thing is extra, which is F. Okay, if F is not given, what do? We have a table. Okay, don't use your brain. We have a table. Okay, that was a message. Some of you start using your brains. Don't. Okay, in the exam I didn't give the level of service table. Somebody still wrote level of service. Like, why? How? Okay, so that question you can do it, right? Okay, everything is given. In this one, we have radius given, and we have super elevation given, and speed is to be found. Okay, so obviously S is missing. S is missing. And what else is missing? Friction is missing. But for friction, we have a table, right?
But we don't have this
We don't have the speed. So now we have to use the brain, right?
assumption.
Oh my god. We assume, right? We have two unknowns. Both of them depend on each other. And there is no other way of finding them. Okay, so we have to assume something. Okay, any value can be assumed. Okay, so for example, I assume speed to be 80. That's it. Okay, so as I assume the speed to be 80 miles per hour. So according to 80 miles per hour, the speed is 80 miles per hour. Then my f value is 0.08, right? Okay. Now what do I do? Next step.
Check
Check
the radius.
the radius. Okay, we can do this. We can check the radius. Okay, or what they have done in the book? They kept the radius as it is. They found f, and then check the f. Anything is fine. Okay, we have three things: radius, which is given, speed, which we assumed, and f, which is according to speed. So again, assumed. You can put any two values and find the third and check it. Okay, so like I said in the book, what did they do? Put speed and radius and find what? F. And f should be how much? Okay. Or what else you can do? Put speed and put f in the equation, find out what? Radius, and radius should be how much? 800. All these things are correct. There is no problem with any of these things. Okay, so whatever you like. What do you want to check? Find the radius. Find the radius. How much is the radius? 3,000. 3,000? 47. So we are very far from the value which is given, right? Very far. It's not even close to 800. Okay, so I should change my assumption. Okay. Yes. We can only reduce, right? This is why I assume 80, because if I assume 50 and it was wrong, then you can go here or there. Again, I have to use my brain, which I don't like. So we assume 80. I have to only reduce. Okay. Now you can reduce 75 and then 70 and then you can keep on doing this. Okay. But I know I'm very far. If I was close to 800, then I know my value is very close. Okay, then I will go to 75 or 70. But now I'm very far, so I can skip 3-4 values and check the next one. Okay, you can check maybe 60 or 55 or 50. What? 50 what? 50 miles per hour. F is 0. How much? 14, and you get the radius as 833 feet. Okay, which is close enough. Okay, which is close enough. That's why in the book they were going with the f value, because in f value there's not much margin. It's already in fractions. So to get the value close is easier. Like something is in hundreds. So okay, but the answer is 50 miles per hour. According to the book. Okay, but if you look at the radius, somebody may say no, it's still 33 feet, but the value is in hundreds and thousands, so 33 feet is nothing, you can accept it. Okay, clear? Okay, but yes, just remember it, huh? Okay, clear. Anything else? Any other bright idea? Huh? Tell me. Huh? Yes, tell me. Exam is what, 2 hours, huh? Tell me.
Where is exam?
Huh? Yes. I'm getting questions, see? You guys are helping me. Yes, tell me. What other way? I tell you Okay, so I said you can check the f values. Since the f values are smaller, so you will have more chance of reaching the exact value. If you are doing the same thing with the f value, your difference will be in points. Okay, but since I am checking the r value, so you can see that even with the final value, the difference is higher. Okay, so always go for the smaller value. Okay, even s is better. Okay, any other question? Clear? Okay. Other important characteristic of the vehicle is the braking distance. Braking distance equals to average speed into time for deceleration, time taken for stopping. Okay. Now average speed. So average speed you can see here. So average speed means what? Final plus initial divided by 2, right? Average is S1 S2 divided by 2, right? Now if I am stopping, my S2 is what? 0. Okay. So this will become what now? Okay. And acceleration equals to what? Acceleration equals to what? Okay, so I will say what? Delta speed over t. Okay, and change in speed, right? So again s1 minus s2 or s2 minus s1 if you are doing deceleration. Okay, but the other one is 0, so this will be what? S or s1. It was s1 minus s2, right? And s2 is 0, so this is only s1. Okay, upon what? Time. Okay, so time equals to what? Time equals to what now?
S over A.
Yes, s over a. Okay, it was delta s upon t. A equals to delta s upon t. Delta s, we have the final speed as 0, so it's only s now upon t. So a equals to s upon t, so t equals to s upon t. Okay, so this is how I got these values. S upon t is basically the average speed, and s upon a is the time. Okay, you multiply both of them, you get s square upon 2a, and we know s is in miles per hour. I have to do the conversion. So after you do the conversion, divide by a, you will get this number. Okay, and the conversion should be square because s is square. Clear? Okay. Next thing is we have a factor which is called as skid resistance. Okay, skid resistance again depends upon the surface of the road, and it is equal to A upon G. Okay, so F equals to what? A upon G. Then A equals to what? G multiplied by F. Okay, F was A upon G, so A is F into G. So this is what we did here. I replaced A with F into G, and G is gravity, I know the value. Clear? Okay, then we will again do the division for the constants, and I got 30 here. Okay, now in this equation you can see I assumed what? First of all, the final speed is 0 and there is no gradient, but we have an effect of gradient, right? The gradient affects the braking. Okay, so I have to include the gradient as well, and the final speed may not be 0. Okay, we will see it. So this is the final equation. Instead of the first one, you can use the last one. Okay, this one. So here you can see the final speed as well. So I can use it for any decelerated value. Okay, from any initial to any final value, and you can see the effect of gradient as well. Okay, so this one is in feet and this one is in meters. Okay, now F was A upon G, right? F was A upon G. Now G is a constant. G is a constant, and ASTO has given us a value for A as well. Okay, so that means I can find out the value for F. How much is the value for F? How much? 0.8. Okay, when you took the A as what? 11.2, right? Okay, so we have value in meter per square seconds as well. Okay, so A can be 3.41 meter per square seconds. Then the F will be what? Same. What? So, should be different, right? No? Same? Everybody agrees? You don't agree? Huh? According to the calculator? Yes, it will be same because we will convert the gravity as well. Okay, so same. So braking distance means the distance you cover after pushing the brake. Just keep it in mind. Braking distance just includes the distance after pushing the brake. Before, whatever you were doing before that, okay, it's not included in braking. Okay. One example now, we have an accident investigator and he found that a vehicle hit the abutment of the bridge. Abutment means the wall of the bridge. And he looked at the damage of the vehicle and he found, or he estimated, that this damage will be caused if the vehicle hits the wall at 20 miles per hour. You have seen those videos, right? Vehicle hitting the wall at 10 miles per hour, 20 miles per hour. No? Check it, it's fun. Okay? Now they are doing it for different companies as well, huh? Toyota hitting at 20, then Honda hitting at 20. Check it.
The video.
Huh?
The video or video.
You are saying what? Check the video. It's his fault.
Give him a bonus.
Anyway, huh?
Bonus.
He will get a bonus death. So 20 miles per hour according to the damage. Okay. So they do these experiments. Okay. Even before the videos they were doing this. Okay. Secretly. But now they know we enjoy these things, so they are earning money. Okay. Anyways. So the final speed of the vehicle at the crash point is 20 miles per hour. Before that point, they saw some skid marks on the road, which is when you brake, right? So the tires make these black marks. So the marks are made when you are braking, right? So you measure the marks, that means you have braking distance. You measure the length of the marks, that means you have now the braking distance. Okay? So what happened? They measured 100 feet of these marks on the pavement and 75 feet of these marks on the shoulder. So there is the pavement, the shoulder and the wall. Okay? So driver was trying to brake, moved 100 feet, went to the shoulder, still tried to brake and then to the wall. Okay? Now the pavement and shoulders have different surfaces now, which is not common. They can be same surface. So the pavement has a surface which has a skid resistance of 0.35. Shoulder has a surface with a skid resistance of 0.25. Okay, clear up till now? Okay. So now we have to find out what is the speed of the vehicle at the beginning of the skid marks. When he started to brake, what was his initial speed? Okay. Now this is the equation we have. Okay. What do we have? Which speed is given? Final speed is given. Okay. So SF is given. And what is the braking distance? Huh? We have to do it twice because we have two different surfaces. Okay. If it was the same surface, we will take 175. But now we have shoulder different and pavement different. Okay. What will come first here? Huh? Shoulder, because we have the final speed which is at the shoulder. Okay. So we have to find out the initial speed at the shoulder. So at the shoulder, my braking distance is 75 feet and the F value is 0.25. So that means my SI is how much? Gradient is not mentioned, so just ignore it.
You mean, the gradient is thrown away, put the 1 without 1
What? Say again?
101.
Yeah, it's just for the percentage. It's just for the percentage.
That's made only 30 by F on the dot.
Yeah. Yeah, say again. No, so now I have initial for the shoulder. Initial for the shoulder means final for the pavement. Okay. So this is now final for the pavement. So what is the initial? So here now the dB is 100 feet. So that means my SF is how much? Sorry, SI. 44.8. Okay, any question? Like I said, we did it like in this way because there are two different surfaces. Same surface, 175 distance and so on. Okay. Now, one thing to be careful about, I use F here, which is capital F, right? Capital F, okay? Which we call as what? Skid resistance. And what are we calculating? Braking distance. Okay. I had another F here, which is the coefficient of side friction. And what am I calculating here? Radius. There are two different values, two different equations. Okay? Don't mix them. Clear? Thank you.